Let's get right into the lesson here. We've got 3 alpha: identify basic facts, principles, capabilities, limitations, satellite transmit receive systems. Just remember you got to score 70% on the tests, which is telling you 28 out of 40. You can't miss more than 12. And I see Airman Liverpool's got your mic.
Yes, sir.
Is there a... Okay, good. So we got Liverpool. Machinsky, are you here?
Yes, sir.
O'Brien?
Here, sir.
Rada?
Here, sir.
Right, I just saw you. Cooper is there too. Daly?
Here, sir.
Senior Airman Ward? Okay, good. And Rosales, I think I saw you too. You're good. Let's continue on. And as you well know, AFSC application, just remember you're going to need the basic knowledge. Now, what we're getting ready to go over is the basic radio picture. Very basic. You can apply this to pretty much any radio that's out there, to include SATCOM gear. And if you haven't figured it out, most of our ground radio folks, which I'm prior ground radio, and we got combined all the wideband and SATCOM into the same group. When I came through in 1987 and 88, they were separating SATCOM away from ground radio. What is it? History likes to repeat itself sometimes. Air Force is good for that. So we're going to look at basic radio picture, the fundamental radio parameters, radio performance assessment, and ancillary functions. Let's go through each one of these. I'm not sure if you have this. I highly recommend that there is one that's coming up in about the next 10-15 slides that fills this in. If you have this breakout, it's a good idea to fill it out. See if you can remember it later on. If you don't have it, I'll try to find you one and send it to you. And on top of that, did they issue you guys any handouts?
Yes, sir. They gave us this handout, which is blank, and then also in the student materials, they have it again.
Okay, good. Good. Fantastic. Thank you. All right, so we can look at the basic radio picture here. We're looking at transmit. Why do we always start with transmit? Well, the biggest thing is normally transmit uses, if you get transmit down, receive uses part of the transmit information. Talking modules or components and so forth and so on. So what is the objective of the transmit? Well, we're going to transmit baseband to the distant end. What is baseband? Well, it is the aggregate that is coming out of the multiplexer. So we talked about multiplexers, good grief, for a while. So now we're going to use it in how do we get it from point A to point B. In our case, transmit baseband to the distant end. It's accomplished in 3 steps. The first step is modulation. Second step is up conversion. Third step is amplification. When we go through the signaling form, the signal flow on the Jerk 239, you're going to hear me say Jerk 239 or Tisser. It's the same piece of equipment. If you look at it above my head, that's what the Tisser looks like. We have a modulator, which is going to take that baseband and modulate it into a IF. Now, I have, at least with this particular system, you're going to see anywhere between 70 megahertz to 30 gig. And again, it depends on what you're dealing with. I've seen radios that are lower. When I say radios, I'm talking like the single channel air traffic control radios. And so they're only in the VHF, UHF realm, and their IF is going to be lower. We also go through an up converter. We're going to take that IF, which is modulated, and we're going to up convert it from IF to RF. Now, how do we get it there? Well, we use something called an oscillator, and we've talked about this before, and we use phase lock loop in order to make sure that we are on frequency and it's stable. So frequency and accuracy, stability do play a part with this basic radio picture. We have a high-powered amplifier, which is we're going to amplify the signal to where we can send it out to point A and point B, and it will depend on what the information and how far we need to go is to determine how much power we need. Next up, we're going to reverse this. So if I get baseband to the distant end's got to do something called recover the baseband. So you've transmitted on one end, now you're going to receive it on the other. So recovering the baseband is done in 3 steps. If you look at this, it is pretty much the transmit except in reverse. We have RF signal recovery, we got down conversion and demodulation. First part, we got noise, a low noise amplifier. Now, if you guys have ever done any DirecTV or Dish Network, they always have an LNA, they always talk about it. Well, that's what it means, low noise amplifier. When you guys get into block 9, you're going to have that too. You're going to have a high powered amp and a low powered amp. This low noise amplifier is going to take our receive signal, which is extremely weak right now, and we got to bring it up enough or amplify it enough to where we can make some use out of it. And the idea here is taking something out of the dirt, is what I like to say, which is near the noise floor, and amplify it enough to where we can pull a legible signal out of there. Next up, we have a down converter, so we're going to take that RF and go to IF. Again, we're going to use a local oscillator using phase lock loop. Next up, we have a demodulator, and this is going to take that IF and convert it into baseband. So amplification, this is the recover the baseband, which is received. So you have RF amp, down convert from RF to IF, and IF to baseband. Demodulation. You'll notice we have this little saying in there, it's called AGC circuit. This AGC circuit is going to make sure that our output is constant. So there is your picture. I'll leave it up for a few seconds here so everybody can see it. You'll notice that coming out of the multiplexer it says MUX. Multiplex, modulate, whatever you want to go, whatever you want to call it, to the modulator to get modulated on an FM signal, because most of, in fact, I'm going to guess with all SATCOM and wideband, they're all FM. I've not seen any, since I've been working this, that has anything different than FM. I can be wrong, but I've never seen one not do FM. So we take the aggregate coming out of the multiplexer, we modulate it, we up convert it from IF to RF, and then RF gets amplified and then out the antenna. The next step is to recover the baseband. So that one was transmit baseband to the distant end. We're going to recover the baseband by bringing the receive signal into the LNA. Low noise amplifier is going to amplify it. We're going to down convert it, take RF to IF. We're going to demodulate it, which we're going to go from IF to the aggregate baseband. We also have this thing called a more detailed showing here. We have a modulator. You'll notice it has a X in a circle. Normally those are mixers. So that's how we modulate. We also have another mixer in the up converter. So we're going to take a local oscillator and get it up to the RF, run through the HPA, and then out the antenna for transmit baseband to the distant end. When we recover it, again, comes through the LNA, going to amplify it. And you can see that there's a trend from the transmit versus the receive. Our LNA and HPA are triangles. When I look at diagrams, any triangle I see, I consider to be an amplifier. And determining what it's going to do will be able to give me some idea as to the reaction it's going to have. So we're going to take a receive signal that's very weak, amplify it, run through the down converter. There's a mixer. You're going to use a phase lock loop oscillator to convert that RF to IF into the demodulator, and the demodulator is going to take it into baseband. So again, this is just a different signal flow, but it gives you a more detailed idea of what's going to happen. Now, we always talk about something called a branch assembly. This thing is comprised of what I call passive electronics. In other words, there's no power being applied to this, but it reacts to the RF. Let's take a look at each one of them after we give you an overview of what's going to happen. So the first thing we're going to look at is direct microwave energy to and from the antenna guide. You're going to suppress unwanted harmonics and external noise, as well as being selected with the frequency. And of course, there is some monitoring to it. We'll go through each one of these. First of all, the arrow in the circle tells you which way the RF is going to go and is going to prevent anything else from getting back in. It's really helpful in the transmit section, so that way none of the RF that might generate a return wave, better known as VSWR, doesn't get back into my electronic section. So I'm preventing a meltdown, so to speak. Because, you know, when we have a mismatch of impedance, which means the antenna isn't efficient, it's not resonant, you know, all those nice little terms that you learned in block 4, it's going to create some heat. So the last thing you want to do is generate more heat to come back into the transmit section. We have directional, or what we call dual couplers. You guys have actually had this in block 1. It's called a through line wattmeter. You'll notice that we have two elements on either side. You had a forward power and a reflected power. Well, this is what a directional coupler does. It's nothing more than what we call an RF diode. It senses the RF and gives a representation of the strength of the signal. So you had an arrow go one way and the other arrow going against it. Well, the forward arrow, which is going out the dummy load that you guys played with in block 1, that was the big strength of your radio. In other words, you should have got either 2 watts or 10 watts in accordance with the way the radio works in block 1. If by any chance that you got some return waves, then your radio is going to dissipate a lot of heat, but your directional coupler is going to be able to sense it. Now, you guys worked with this in block 3, which means that I think it's when you're in a 10 watt mode and you get a high VSWR of 3 to 1, the chance that radio is going to react and bring it down to 2 watts. And the whole idea behind bringing it down to 2 watts is so you don't lose most of your communication. Because the last thing you want to do is be in combat, your antenna gets blown off, you know, it's only half of it is still there, but you're still able to transmit and receive, but just at a lower level. So it just goes to show you they did think about these things when developing that VSWR and using the directional coupler. Those are normally internal to the transmit side, but it does have a function on the receive side, believe it or not. Let's just say that you've got 2 radios and they're side by side. You key one up and you don't hear anything on the other radio. Well, that's because the directional coupler just muted the receive because there's too much RF coming in. That's what the directional coupler does is it mutes it if there's too much RF coming in. Here are some pictures of the next one that we're going to be looking at. It's a duplexer. I've used both of these out in the field, and the duplexer on the left-hand side when I was playing around with my satellite TV. This is a more recent upgraded version, so to speak. This is what they use. Well, you can go to Walmart and buy one of these. So we look at filters. This is the box with three horizontal lines and 2 diagonal lines. And the idea here is we only want the frequency that we're going to need and block everything else. That's the whole idea. Circulators, that's pretty much the diplexer and duplexers that I wanted to show you. That was kind of silly. This. Okay, good. I got them out of sequence. I don't know how I did it. Okay, circulators. These are the really weird ones. Normally these things, depending on where they're located, have a 3 or 4 points on them. And if you look this up under Google, again, they work passively. But with our SATCOM or wideband, what you're going to see is our transmit frequency is different from our receive frequency, so we don't interfere. Well, with this circulator, because that's what that is, our particular circulator has a 3-point system on it. It knows transmit, and it's going to direct it out the antenna. At the same time, it knows receive, and it's going to direct it into the receive section and keep them separate. Now, when I last looked this up about 2 weeks ago, it looked like there were ferrite core beads that they'd wrapped not beads, but looks like washers, thick washers, and they would wrap the coil around them. And this is how they are able to differentiate between the transmit and receive, and it works by itself. There is no power or anything else that, or magic dust, so to speak, to make it work like it does. They're able to use the impedance on the antenna to determine whether, which is transmit and which is receive, and keep them separate. This is basically right out of Google, the picture. In our case, we're going to have a 3-port system. Passive, non-reciprocal 3 or 4-port device in which a microwave or radio frequency signal entering the port is transmitted to the next port in rotation. In other words, it's able to decide which one is transmit and which one is receive. Crazy stuff in this equipment. Next up, we have something called Rago. Let's go through it. R is called receive signal level. That's the strength of the signal that you are picking up from your antenna. AGC in voltage is going to react like the RSL is doing. And then we have gain. Okay, there's got to be some type of proportional items that go to the gain in relationship to AGC and voltage. And then lastly, output. So let's go through the boxes here. RSL, your receive signal level, is going up. AGC is also going to go up because it represents the receive signal level. At that point, gain is going to go down because the strength is getting really strong, and I don't need that to be getting stronger, so I'm going to start taking the gain down so I keep the output constant. Let's reverse this. Receive signal level is weak, so my AGC is going to represent it, so therefore it will be weak. Then you have gain Well, since it's so weak, I got to bring it up. The idea here is to keep my output constant. Now, it's been many, many years of keeping the same sequence of events with me. Anytime I see AGC, I automatically think receive. I've seen transmit where they use different acronyms to give a constant wattage out versus a constant output, which is audio or digital data or digital. So the idea here is anytime you see receive, think receive. Let me give you an example of how this is turning out to a situation that I can give. I worked in the air traffic control tower, or in the air traffic control environment, and repairing the equipment. And the easiest way to explain AGC is when the air traffic control receives a signal from the plane, depends on whether it's out or close, will determine the AGC level. So let's go with this. If the plane is 200 miles out and it's transmitting to the base and you did not have any AGC, the air traffic controller is probably going to have to turn that volume control switch maximum to hear that plane. As the plane gets closer, what's going to have to happen is he or she is going to have to turn the volume control down because it starts getting louder. And of course, let's do the reverse, if you got a plane sitting on a runway getting ready to fly off, it's going to be maximum, so you're going to have to turn the volume down. As the plane goes out further, when they're still talking, you're going to have to start turning that volume up. AGC substitutes the human portion of that. The idea is to keep your output constant, so that way you're not have to constantly finagling with the volume control button. You can also do radio stations the same way because it has AGC in there to begin with. In other words, let's just say that you're here in Biloxi, Mississippi, but you're going to travel to Mobile, and you pick a Mobile station up. Well, as you get closer, the signal is going to get stronger. So the AGC is going to make that output constant, so that way you're not having to crank up the volume. And as you come back from Mobile, the signal is going to get weak, but since AGC is there, you don't have to turn the volume up. Let's take a look at all these different terms that we have coming up on fundamental radio parameters. We have frequency accuracy, stability, bandwidth, frequency response, selectivity, gain, and sensitivity. Let's take a look at these. Frequency accuracy and stability depends on the oscillator. Phase-lock loop is what keeps it accurate. Bandwidth. Well, we've already gone over a couple of this. It could be the upper and the lower end of the frequencies, or it could be the amount of bandwidth needed for a digital signal. It just depends on how you're going to use that. Next up, we have frequency response. Now, I'm reading this one. Okay, it says the frequency range over which an audio device or system will produce or reproduce a signal within a certain tolerance. Now, most of you are going, okay, what does that mean? Back in the day when you had stereo systems, one of the first things I normally pulled out was looking at the frequency response of my audio system. Normally, it was anywhere from between 0.05 and 0.01%. Normally, I would want the 0.01. What does that tell me? Well, when I'm playing an album or a CD or a tape, I know back in the day, that music is going to be almost like I was sitting in a concert hall and listening to it. Now CDs are crisp because they've actually lose a little bit of the audio because of the sampling. Remember, the more you sample, the better representation of that signal will be. However, processing speed with that. Next up, we have selectivity. This one is the desire to snag that one frequency and get rid of all the others. In our radio systems, we normally have what's called a pre-selection. In other words, we take the full radio spectrum and narrow it down to a small range of frequencies. And then we have overall selectivity, which takes that small amount of frequencies and cleans it up to get just the one. Next up, we have gain. This one is what I like to classify as your volume control knob, or whatever you need to do to amplify it or turn it down. Sensitivity, how well you're able to do the signal plus noise to noise ratio, just like you did in block 3. In other words, you measured the signal and the noise together, and then you used the boomton, if I'm not mistaken, and you canceled the signal, i.e. the 1 kHz, and you looked at the noise. It should have dropped at least 10 dB, if not more. Anything more than 10 dB drop or less than 10 dB drop, you got a problem with your receiver. Next up, a systems approach. Let me try to explain the systems approach. You do not know how many times that I've had to troubleshoot other people's equipment because it didn't work correctly. Yeah, you're going to go out there, somebody calls you out and says, hey, your equipment's not working as advertised. And you go out and you find out it's working just fine, but it's the user or someone else's equipment that's causing the problem. Normally when that happens, that's called troubleshooting the system. Just because your equipment works doesn't mean the system works. But by finding out in process of elimination through troubleshooting, you'll be able to determine, is it my equipment or is it someone else's equipment, or is it the user not operating it properly? By the way, anybody in here from maintenance in the past? Daly, Ward, Rosales, any of you guys in maintenance?
Yes, sir.
Yes, sir.
Did you catch that part about the operator?
Yes, sir. Like I would like to say, majority of the time when I'm always out there, it's always them usually, not working the equipment properly.
That is correct, and I'm going to piggyback on that, because when you say it's operator error in the coding, when you put it in, you really got to justify that. They don't want you, the maintainer, telling somebody's operator they don't know how to work the equipment, because what that means is it's a training deficiency, and people really take a look at that, a hard look at that. So be gentle out there. Normally there's a thing called no problem found code. You guys will get to it when you get out in the field. That's one of those things you'll be trained on. Next up, we have performance measures, quality, reliability, and speed. So let's take a look at those. Here are the definitions. Quality, how closely the output resembles the input. That's pretty clear. Reliability, how well your equipment is performing. In other words, the uptime. Speed, how fast your equipment can process the data, as well as being able to get COM up quickly. We have switching, auxiliary channels, and performance monitors and fault indicators, all under ancillary functions. You're going to see this on the Jerk 239 TISR. Let's look at switching and auxiliary channel. Switching, the idea is if one goes down, hopefully it'll switch over to another piece of equipment. The idea is you don't want to have your equipment down for any length of time. Next up is an auxiliary channel. What does it mean by an auxiliary channel? Well, we as maintainers normally get an auxiliary channel, at least with the TISR, and if I'm not mistaken, with the SATCOM stuff. We don't get it with the radios, unfortunately. But an auxiliary channel is you're not on someone's pieces of equipment. You're off to the side being able to do what you need to do. It doesn't affect what they call the aggregate, the digital information needing to go from point A to point B. And you're going to see this when you set up the TISR, because we have an auxiliary channel on the TISR. We have performance monitors and fault indicators. Take a look at these. The idea behind performance monitors is to see if your equipment is starting to fail or if it is on point. Normally PMIs, preventive maintenance inspections, will help you out in checking to see if your equipment is doing what it's supposed to be doing. If not, you might have to adjust. If not, your equipment's probably getting ready to toast out, and it's better to catch it before you get called 2 or 3 o'clock in the morning and have to go out and fix it. Now, with fault indicators and that, I usually, when I'm doing troubleshooting, and I'm sure Senior Airman Daly, Senior Airman Ward, and Sergeant Rosales can probably tell you that those are the easiest fixes if you focus visually on your indicators. With the TISR, it's pretty easy. If it's a red light, you got problems. Or if a light that's not normally on, illuminates, yeah, you got a problem. Okay, those are some items. For example, I worked in the air traffic control environment, and we had receivers, single channel receivers, and we had single channel transmitters. And when I got called out at dark 30 in the morning, first thing I would do is I would keep the lights off, walk in, look at all the equipment, and find out which one of the lights was off. At that point, it's pretty easy to understand how to fix it. And of course, that's your visual inspection. Fault indicators are wonderful, and you're gonna probably rely on some of this information when you get to the TISR, because if you're having problems with communicating to the distant end, your fault indicators as well as your performance monitors is going to give you an indication where the problem lies. Excuse me. So we've gone through basic radio picture, fundamental radio parameters, radio performance assessment, and ancillary functions. Any questions? I know it's pretty quick. Give you some time to digest. I do have a
No, right
question.
now, sir.
Okay. Senior Airman Ward, what did you do? Linguist. Wow. That's impressive. What language? Whoa. Yeah, they need the Arabic. Need the Arabic. When I came in, they wanted me to go to linguistic school and for German. Just because my last name is German doesn't mean I can speak it. That was kind of interesting on that test. All right, so, okay, yeah, no German missions now. That is true, because German is an ally now, and most of the Germans can speak English just as well as we can. All right, let's take a look at the objective 3 Bravo. Dating yourself? Yeah, probably. Yeah, I'm old. I came in a very long time ago. 3 Bravo, basic facts about principles, capabilities, and limitations of modems. I'm not going to go through the testing. I think I've emphasized that enough. We're going to be looking at dealing with networks and modems and how they all fit together. We're going to look at general modem principles, types of modulation, forward error correction, interleaving, traditional modems, and IP-based modems. Take a look at this. So what is realistically a modem? It is easier to get a digital signal from point A to point B if you modulate it into an analog carrier. You guys have been doing this believe it or not, with the Prick 150. It's taking your analog voice, converting it into digital, and using the RF portion to get it to the dissonant. As you well know, if you watch the History Channel, between, the fight between Edison and Tesla, yeah, DC doesn't go very far and requires a large amount of equipment to get it to work. Thicker cables to get it from point A to point B, where AC, you can go pretty far distance before you have to amplify it. We're going to be looking at baud. This is your speed of bandwidth per signal, known as a symbol. We have bit rate versus baud rate. You guys do know that an 8-bit word versus baud, I think there is a significant difference of how many bits can be in a byte, so to speak. And today, that 10 bits per symbol, when they made this, yeah, it's pretty wicked, in my opinion.
Sir,
Yes.
I'm kind of confused as to why we have the baud rate. Isn't it just talking about bits per second?
When we get into taking a look at converting everything into a baud rate, we have to have 3 of these things. It's just leading up to it. Now, when you get a piece of equipment and your baud rate is this, or they say symbol rate is this, you know that there's some interchangeability there. It's just to give you an idea, because we're having to deal with, and this is the Air Force as a whole. You have old equipment, you have new equipment, and everybody's going, why don't we get the new equipment? Well, we're the stewards of the taxpayer money, so we have to interchange some of the older terms with the new terms. So when you get out in the field, you have no idea if it's going to be an old piece of equipment or a new piece of equipment. This is what's leading up to, when we do the bit rate, baud rate, and so forth and so on. This is how they wanted us to teach this. Okay, we are basically the individuals that just have to deliver what the senior leadership wants. So when we look at baud rate or bit rate or bytes, so to speak, they're not interchangeable, but they're relationships to it. Bit, which is 1, it's either a 1 or a 0. Byte is, how many bits are in a byte determines the word. And then when we look at symbols or baud rate, that's, okay, how much is in that bunch of information to include overhead. So that's what we're trying to lead in, just building blocks to where you understand this enough to go, okay, we had this, I kind of understand it. Google is wonderful at times. For those of you that don't do Google, suggest that you do like DuckDuckGo. There's a couple others out there that do not track you unless you tell them to. Google will track you.
Sir.
Yes.
So basically, it's like how much information it can be pushed down the bandwidth per second, right? So like,
yes,
there could be, so one bandwidth could have 1 symbol per second. One could have like a couple symbols per second.
Or we're going to get to that in just a few. So you're trying to steal my thunder here. Yeah, you're getting ahead, but yes, you are correct in saying that. So we got to take what we in the older pieces going to the newer pieces, and I'll try to draw that relationship. Hopefully this will answer your question, so give me some time here. We're going to look at types of modulation. We got frequency, amplitude, and phase. So let's take a look at frequency. The easiest way to describe frequency is the Morse code back in the day, or teletype, being able to distinguish what's ones and zeros. FM, I like to call it FM. It's 1 bit per symbol. let's take a look at the actual diagram itself, or the frequency. You can see where anytime that you see a 1 will be one type of frequency. In our case, we're showing it to be a higher frequency. And anything that you see zeros to, you will see a lower frequency. Now, it doesn't distinguish between the two zeros. It only changes whenever there is a different number that comes into play. So ones and zeros are interchangeable when it comes to staying the same frequency. So you can see we got 2 zeros in a row, we have 2 ones in a row. The frequency never changes. Kind of looks like NRZ, doesn't it? Next up, we have amplitude shift keying. This is also 1 bit per symbol, and again, it's going to differentiate between what is a 1 and what's a 0. Again, let's take a look at the figure. You can see that anytime we have a 1 higher number, you have a bigger amplitude. Anytime you see zeros, you have a lower amplitude. So those are the variations, and you can see that our data signal, so to speak, you got 2 zeros in a row, then we have 2 ones in a row. They don't change until it changes the logic. Again, FM and ASK amplitude are 1 bit per symbol. Next up, we got phase shift. Now this one starts getting a little bit elaborate. The first one we're going to look at is binary. This is also 1 bit per symbol. Let's take a look at it. Binary is going to shift the phase of the signal, not the amplitude, not the frequency. In this case, we got a 0 phase shift with, when you don't change the logics. You'll have 180 degrees phase shift when we do change the logic. So in other words, 1 to 0 or a 0 to 1. Again, 1 bit per symbol. So those are the 3 that have 1 bit per symbol. This is BPSK. You can see that every time we change the logic, in other words, a 1 to 0, you'll see that we have a phase shift. From a 0 to 1, we have another phase shift. Let's look at quadrature. Now this one's kind of crazy. Now what does it mean by 1 bit per symbol? Well, it's either a 1 or a 0. With quadrature, and this is where the 2 bits come into play, and you can see the box below it, that's the how many bits it's playing with, or symbols. You've got a 0 0, a 1 0, a 0 1, and a 1 1. In other words, when you're looking at 1 bit per symbol, you only have 2 different states it can be in. With quadrature, you've got 4 different states it could be in. So that's the advantage of 2 bits per symbol under quadrature. If we go to QAM, holy crap, because this gets into some calculus that is a whole new, I can't even explain it the way they explain it. Normally I know the instructor's name or the professor's name when they're doing it, and I kind of understand about the first minute or two. After that, it's beyond my capability of understanding. But you can see that we have a XY axis, and it's divided into 4 different parts. So that's where it's getting the 10 bits per symbol. And the way this is done is crazy. So let me go back up to this one, the quadrature. The reason why you can get 2 sets, in other words 2 bits, is because it has, believe it or not, 2 carriers in the same signal. With quadrature, there's 4. And it can get even crazier than that. The reason why they've gone to QAM and are so big on it is you can add more and more to it. So it could probably exceed more than 10 bits per signal by now. But you deal with, and I'm going to give you the idea behind TVs. You're going, what does that got to do with anything? Well, if you're streaming let's just say you got Netflix and you have a 1080, you're probably going to get 1080. That's 1080 lines per second. Okay? What does that mean? It means it's a better picture. Well, you do know that they have 4K out there. The problem is the capability of the internet. You can't get 4K on the internet yet. Now, if I'm not mistaken, with this Google Fiber going in some places, they can do that. But I have yet to see it. So as far as 4K, that's 4,000 lines per second. What does that mean? It means the picture's getting really clear. And if you add in the new features such as OLED, which is organic, and then you have quantum LEDs. And depending on your preference, pick and choose. What does that mean? It means the blacks are blacker, the whites are whiter. You have better vision during the daylight as well as nighttime. So there are some plays between both of those, so you can look it up. But as far as I'm concerned, I really don't want to see the actors' faces with, fill in the blanks. It's like you being really close to them, be able to see the maybe a scar that you didn't know the actor had, or a tattoo that the actor didn't, that you didn't know had. Just you see a lot more when you start adding more lines of resolution in the TV. Now, when you look back at over the air, you're looking at, 480, 720, and 1080. Most TV stations are doing the 1080. Some are still doing the 720, but your basic LCD is somewhere in that 480 and works its way up. I know, it's kind of crazy. What does QAM have to do? Well, QAM is part of that 4K. They're working on 10K now, especially in Japan. And that's ridiculous. So, is our internet going to be able to keep up with it? Probably not. When we look at this, we also have something called forward error correction along with this information that they're going to be sending, either ASK, FSK, binary, Quadrature, or QAM. So out of those 5 that I just told you, 3 of them are 1 bit per symbol, which is the amplitude, frequency, and binary phase shift king. But when you get into the Quadrature and the QAM, 2 or more, all the way up to 10. In order for us to help ourselves get that information to the distant end, we use something called forward error correction. Now, the easiest way to describe it is the transmitter. Let's just say that you're sending some information to the distant end on your computer, and it's important that you get that email with this document to it. And when you send it out and it's all on, let's say, standard copper twisted pair to the distant end, you're probably going to get some noise and you're going to have some issues at the distant end and being able to put everything back. But with forward error correction, it will help you be able to decipher what got there and piece together all the information logically. I call it the Wheel of Fortune at the distant end. That's basically what it is. If you're missing a couple pieces of information by sending one of those forward error correction portions to the distant end, then you're able to decipher what it could be. Because you guys all have seen Wheel of Fortune, where they, they're the end of the show where they do the wheel, and they give them the vowels in one, or I think it's 3 constants or something like that, and then they add theirs in there to see if they can name the word. Well, that's basically what forward error correction does. So they have forward error correction rates. looking at 1/2, 3/4, 2/3, 5/6, and 7/8. Well, what does that got to do with anything? It means that the first number tells you how many bits of information was there and tells you the number bit that the forward error correction is going to have. Now, if you were to look this up on YouTube or any other place, you're probably going to find something called Hamming code. Hamming code. Again, that's one of those where the instructor, I know their name after about the first 2 or 3 minutes of them factoring in, then they go off on a tangent and I lose that after then. But it's basically that error code helps them be able to piece together the information that was sent and be able to put it together, like I said before, the Wheel of Fortune at the end. So 1/2 means that the first bit is information, the second bit is the error code. In other words, 2 bits are being sent. One's the intelligence, the other one's the correction. The 3/4 means I'm sending 4 bits. 3 of them are the intelligence. The 4th one is the error code. Same with 2/3, 5/6, and 7/8. So it just goes to show you how the forward error correction works. Now, the idea behind this is we got to figure out baud rate or symbol rate of our equipment. There is a mathematical equation. I'm not sure if he still kept it in your study guide workbook or not, but it's able to factor out how you get data rate, modulation type, forward error correction into baud rate or symbol rate. This is a block diagram of how it all works out. First of all, you have the data rate, which could be coming from your multiplexer, going into the modem. Modem has a forward error correction to it. Then it determines what the modulation type. You got FSK, ASK, either binary, Quadrature, or QAM. And by doing this, you'll be able to figure out what the symbol or baud rate is. Again, there's going to be a lot of information going down that line. It's going to get crazy. But the idea here is to figure out how do we get symbol rate or baud rate. There you go. You need data rate, forward error correction, and modulation type. Those are the 3 ingredients. Now, they do have another form of forward error correction. This one's called interleaving. I'm not going to go into it. The idea behind it is when you're sending out packets of data, there is the possibility that you could lose a whole block of it. So the idea here is by interleaving or interweaving, it's not interweaving, excuse me, interleaving or mixing the forward error correction in there, you're able to retain that whole block instead of losing it. When I say whole block, there might be a couple pieces missing, but with the interleaving, when it gets put back together, instead of losing the whole 8-bit word, you might have 1 or 2 bits that are missing that you can figure out using the forward error correction. Next up, we talk about traditional modem types. You got telephone modem, satellite modem. Telephone modem, remember the old 56K? Well, there you go. Satellite modem. We have one, and I'm hoping that you guys did when you walked into room 116 to work on the NSM, looked off to the left, and you saw the iDirect. That's a satellite modem. We have fiber optic modem. Now this one requires us to know the 5 stages, which are stage 1 is a modulator, stage 2 is a transmitter, stage 3 is receiver, stage 4 is a filter and demodulator. In other words, it's taking from the transmit side all the way through to the distant end and how it gets there. Next up, we have an IP modem. This is basically what we have today. Instead of having to dial the distant end, now it's constantly linking. Here's your iDirect modem. It gives you a brief overview of what it is. We do not have this for our test because It's really hard to decipher where that information is. Luckily, this is straight from the manufacturer. We just want you to know this portion of it. But this is the key part in what bands are it? What bands are the iDirect modem working on? You have the C band, the X band, the KU band, and the KA band. For those of you that know the frequency spectrum, you'll notice that starting with the C band all the way through the KA band is approximately 2.3 all the way up to 40 gigahertz. Yeah, it's up there. Now, the easiest way to remember this is you're thinking bands, B-A-N-D-S, like Styx and Led Zeppelin and whatever you guys are listening to nowadays. But Sergeant Young came up with this as far as the bands. You have the CX Kuka bands. All right, Sergeant Senior Ward. Yeah, but I still love their music. But that's one way to remember it, is the CX Kuka band. Now, with that in mind, you're going, okay, KU and KA, where's there a K band? Well, there is a K band. We just don't use it on that modem. Well, what's the KU and the KA stand for? KU means it's under the K band as far as frequency is concerned, and then KA is above the frequency. So it just gives you an idea how well, how to remember it. Big thing is, it's a satellite modem, and it operates on the 4 bands. Yeah, it's clever. I can't claim it. That's the reason why I say Sergeant Young was the one who introduced me to that. So next up we have the general modem principles, types of modulation, forward error correction, interleaving, traditional modems, and IP-based modems. Any questions on that? I know it's going to take some time. I'll do my best to get this up online today, or tonight would be a better way of saying it. So here's what we're going to do. See, that's 3 Bravo. We're going to do 4 Alpha. Let's take a 5-minute break. Come back at, I have 10:02 right now. Let's come back at 10:07. All right? Break.
Yes, sir.
Everybody have a good weekend?
Yes, sir. Had a good weekend.
I mean, it was 4 days. That's a lot of game playing there.
I used World of Tanks. I definitely got some stuff upgraded.
Yeah, they had a lot of discounts. And I got a new tank. Well, I actually got 2 new tanks. And added all that stuff, so
I think I got 3, and I'm almost working on, or I got 2, and I'm working on the 3rd one right now. I almost got the 3rd one.
I'm more of a collector, and then I'll figure out which tank to play later on. I like my IKV 72 Tier 3, and I was able to ace tank it, and when I did it, apparently, I didn't know that you could do this, I set a new record with that tank on damage.
What new record?
Damage. Like 1,700 in damage.
In one game?
In one game. And it was a draw.
Holy crap.
Yep. And then about 5 games later, I aced it again with damage of 1,300, but I had a whole bunch of spotting assist.
Man, you were rolling.
Yeah, it was about 2 weeks ago. But with the ×5, I was trying to get all my crews. That's the best time to do your crews. You'll take one tank, you get the 5, the ×5, go through all your other tanks and try to get, your crew upgraded. I didn't get through all of them. I was only going through the ones I wanted to get upgraded. And doing that, I found out I had, of all the things, a Valentine 2 Russian tank, tier 4. I'm working on their 5th skill level. Like, I didn't even know I could do that.
Wow.
Yeah.
Yeah, I'm trying to get to the Russian, the KV. Right now I have the KV1, but I'm trying to get to the KV2.
Okay. I've
And
got.
I'm having trouble with the KV1 because it's so slow and the fire rate's lower. And it seems like every game I play with that tank, I lose.
Oh. Well, if you just recently take it out, you're going to do that a lot.
Well, no, I have it. I have it almost completely upgraded. I mean, I could have it. I'm just working on getting to the enough XP to get to the KV2 right now.
Ah, okay. So you don't
But and then
max train your crew while you're doing it.
no, I just kind of level through, and I almost got to right now I like the T1 heavy.
Mm-hmm.
I love that tank. I have that fully maxed out, and I actually got XP enough to get to the M6, but I don't have the coins for it or whatever. So I'm just trying to get enough coins to get to the M6 right now.
Okay. Yeah, there's a lot of those M6s out there. Gotta love the American line. My main lines are the American, the Russian, and the German. I've been having really good success with the German line for some reason. Even though the guy.
I'm the same. I have the tank destroyer line on the Germans. I got a heavy and a medium in the American, and I'm going heavy in the Russian.
Okay. I could talk tanks all day long. Oh well. Let me get this going here. Let me change this to where I can. And that's this. I don't know why, but PowerPoint loves to do this. I'll go through 4 or 5 different PowerPoint files, and then I'll find like 3 or 4 of them that do not center themselves. So I don't know why. Every one of them is 108%, so I can match it on OBS here. So I'm at a loss. All right, so let's look at identify basic facts and principles about principles, capabilities, limitations of a line of sight radio system. Yeah, this is a little bit different than our block 4. Line of sight in block 4 was, obstructions could impede your, and we always talked about omnidirectional antennas or bidirectional antennas. Well, now we're going to be talking about a unidirectional antenna. So therefore, when you set these things up, if there's anything in the way, you're not going to communicate, period. There is no diffraction or reflection or multipathing. You just don't have any comm until you get it dead on to the distant end. So we're going to look at line of sight principles, repeaters, and limitations of repeaters. So this is a definition, pretty much resembles the one from block 4. But the key part here is if you can't see the antenna optically at the distant end, you have a very good chance of not being able to communicate with them. We have, and this was up in Fort Gordon, off to the left there on that picture. They call those the Mickey Mouse ears. I got to see a lot of that when I was up there learning some of the SATCOM gear. This is straight out of, I think it's pretty much page 1 of your electronic C's and D's. Electronic. C's and D's. Hang on just a second. Okay, this is what you'll find in the testing lab. And I think it is the handout 3D133-7-5. And I'm not sure if you can see this, but you'll notice right about here, down below it, it shows percentages. So I highly recommend that you open up those C's and D's. Let me see what the actual name of that is. It is the same number. There you go. Not sure if you can see the bottom portion up there that says you can see true Earth radius. It'll show you the diagram for true horizon versus optical horizon. That's 18%. And between optical horizon and radio horizon is 15. But your true horizon to radio horizon is 33. So you're basically adding 18 to 15 to get you 33. But this is in your electronic C's and D's, better known as the 3 Delta 133-7-5. It'll say circuits and diagrams, Tropo satellite support radio, TISR PDF.
Is the true horizon, is that just like what your eyesight can see?
Well, optical horizon's 18% further than true horizon. And that's where the curvature of the Earth starts. And then optically, you can see past it just a little bit more. Now, as far as radio horizon, we always talk about the, what do they call that? Surface waves, where they're electrically coupled to Earth. There you go. That's how far the radio horizon goes. It also has to do with, oh geez, what's the name of it? When you go out so far, it gets weaker and weaker and weaker. Path loss, there we go. Path loss. So that also plays into the radio horizon. Frequency plays into radio horizon. So when you look at true horizon versus optical versus radio, take it with a grain of salt. I always like to say, if you ever come out of White Avenue Gate, what does that mean? Does anybody not know where White Avenue Gate is? That's the one where you come out and you go down you go over the railroad tracks and go down to US 90. Well, if you're up on top of that little crest and you look way out there, you can see one of the islands, and that's about 14, 15 miles out there. You can see, your optical horizon. You can see the trees that are out there. Can't really see too much of the island. You won't see like the sands and all that kind of stuff because it's too far out there. But it just goes to show you that, this does play a part in the way we look at line of sight. Hope that answered your question. I still remember while I was stationed at Hill Air Force Base, they had something called Antelope Island. And if you were on Interstate 80, which stretched from Reno, Nevada to Salt Lake City, there's basically one straight shot, about 200 miles of maybe one gas station in between there. When you get to the Great Salt Lake, you will see an island with a big mountain on it. it looks relatively close. We had, during that time frame that I was stationed there was a newscast out there that rescued 3 tourists in the middle of the Salt Lake City, or Salt Lake, the Great Salt Lake, and what they found out was they went for a swim. They were going to swim to the island. Island's 18 miles away from where they were at. So you can see the picture of what you're actually seeing versus how far it's out there. That's pretty far. 18 miles. And they were trying to swim it. Line of sight principles. We have a typical range of 20 to 50 miles, frequencies 3 to 50 gigahertz, and powers 1 to 5 watts. Typically. We're dealing with our everything from microwave shots to SATCOM scenarios. Why do we have line of sight radios nowadays? And we're talking more along the lines of our unidirectional equipment. We're not talking about the omnidirectional or bidirectional or long haul capabilities, but we're looking at, okay, how do I get from point A to point B on the base by using, let's just say, the TISR. The idea here is I don't want to dig cable. I do not want to dig a ditch and put the cable in. Okay? Or the terrain, because of it being rocky, the equipment won't work. You won't work because you can't dig in rock. No shovel will get through it. So that's one way to look at it. Or you need to get up and over a mountaintop. Or you only need to go like 10 miles, but hey, I'm not going to dig cable for 10 miles either. Now, how does the repeaters play into it? Well, if you got to get up and over a mountain, in other words, from point A to the top of the mountain and then back down on the other side, a repeater is a good way to go. So it's extending the distance for your communications. And you guys had repeaters back in Block 5 for the LMR systems. Repeaters, we have 2 things that they must do. Transmit and receive, but the biggest things are frequency translation and amplification amongst those 2 items. Frequency translations is once I receive the frequency, I got to convert it into something different so I don't interfere with that frequency. And as you well know, when you receive a frequency, it's pretty darn weak. So I need to amplify it. So those are the 2 things. Now, there are 4 types of repeaters that we go through. It's the RF and the IF. Baseband and audio repeater. But the 2 that we look at are the RF and IF repeaters. Again, your electronic C's and D's has the 2 repeaters on them. 2 of them. That's information that you might need if you got a question you're trying to find, and it could possibly be only on that page. So let's take a look at the RF repeater. Well, what 2 things must it do to be classified as a repeater? Well, frequency translation is the first one. Well, you'll notice that we have 440 megahertz coming in on our receive. We're going to take it, convert it into 4660 megahertz. So there's a frequency translation, or what I classify as frequency conversion. The next one is amplification. Well, when I receive it, the first thing I got to do is amplify it. And then when I get ready to retransmit a different frequency, I also have to amplify it all the way up to the operating capabilities or the wattage capabilities of the equipment. so I can get it to the dissonant. So that satisfied the two items that I need to qualify as a repeater: frequency translation, amplification. Now the problem with this is, because it's still in frequency form, it's going to introduce a lot of noise. Why? Because you had two amplifiers in there. It's going to amplify not only the receive signal, but it's also going to amplify the noise. So that's the reason why it says introduces the largest amount of distortion amongst the four repeaters that we go through. We have the IF repeater, which is going to break it down into the IF section. Let's take a look. So you got 440 coming in, received, gets amplified, then gets down converted to 70 megahertz using an oscillator. Because we manipulated the signal, we're going to amplify it. Then we're going to take that 70 megahertz and convert IF to RF. Now during this process, there's filters in there too, so you're going to eliminate a lot of the noise when you compare it to RF. So when it transmits out, again, it's got to be amplified because you manipulated the signal to 4660 megahertz. So there you have your two basic requirements of a repeater, which is frequency translation and amplification. But this one breaks it down into the 70 megahertz.
Sure.
Yeah.
Are those local oscillators? They're not fixed, are they?
Normally they are, unless you change the frequency receive and transmit. When I say fixed, is there's no way to get in there and you manually change them. So to answer your question is, and I'm thinking, okay, when you flip the thumb wheels on your front panel, you're actually changing the oscillator. That's the only way that you can change it. If you're looking at if it varies or anything like that, it shouldn't. That make sense? Probably not. Yes, no, maybe?
I'm still kind of confused.
Okay. When you set this up for your frequency to repeat, once you've set it up, you should never change it.
So with the repeater, you should only use one frequency with that one?
Well, it's actually two. You're going to have a transmit frequency and you're going to have a receive frequency.
But to transmit to the repeater, you only use the one frequency. If you want to use a different frequency, you got to change the repeater's oscillators.
Well, when you change the frequency itself, it changes the oscillators. Okay. Think of it this way. When you have, there's one portion that's receive, and then there's a portion that's transmit. The front, let's just go with your LMR systems. Okay, you got a base station. Base station does transmit and receive. Well, you can set those things up as repeaters. It's been a while since I've done it. But you can have a transmit function on one and a receive function on the other. In other words, you've got two separate entities. When you program it in, you say, I want it to transmit or receive this frequency. The local oscillator sees it and changes its frequency accordingly. When you go to your receive, it's also set up the same way. Once you program those in, they never change. So if I'm receiving 440 megahertz, what you told that receiver, that's the oscillator that's going to generate that to break it down into 70 megahertz. Once you've done the transmit side, it's also going to change that oscillator to that whatever the frequency it needs to convert it to the 4660. In other words, you have two separate entities. In other words, you're not taking, it's not one piece of equipment that has only one oscillator in it, which would be constantly changing. This actually has two pieces of equipment with two separate oscillators in it. Maybe
So
I'm
you're saying is,
misunderstanding.
so the oscillator, so with if you send a frequency to the repeater, the oscillators will change automatically, or do you have to manually change them?
You have
It's
to
kind of
manually change it. Okay?
so if you send a frequency that's not what you manually changed it to, it's going to be off because it's not going to get that set of megahertz, 70 megahertz.
It will not work.
Okay, so that's what I was. Okay.
Okay, so good. All right. Yeah, you're thinking, because, you know, if one end is transmitting 440 megahertz to get to the repeater that's on top of a hill, you're going to have to program that repeater on the receiver portion 440 megahertz to receive it. On the other side of the hill, you're going to have one that's transmitting, and it's going to have to change to 4660. So there's basically, it's two pieces of equipment that you're using to make a repeater. We used to do that when we had enough equipment, where we would set up at Foster's, program in a multiplexer that had a phone connected up to the Jerk 239, the Tisser, and send it to the Levitol building, where you would have two Tissers side by side, and they were connected. And they would take that information, convert it, and retransmit it to Jones Hall. Jones Hall would take that receive information, run it into the SATCOM, run it into that SATCOM, transmit it up to the SATSIM, and it come back down. And they would do a phone call transmission between Foster's and Jones just by using that equipment. Now, granted, it was 4 separate pieces of equipment, but it gave you an idea of how a repeater works. Again, once you set the frequencies, the oscillators are set. I hope that makes sense.
It makes more sense, sir.
Okay, because in the back of my mind, I've set up many a repeater, both radio and this particular piece of equipment, and they work quite well. So just to give you an idea, can you set up a repeater for both UHF and VHF? The answer is yes. Wait a minute. They don't cross. Like, yeah, they do. You just got to make sure you got one piece of equipment that does nothing but VHF and another piece of equipment that does nothing but UHF. You can make it work. And just like this does. So it's crazy how repeaters work and how well you're able to do it. To give you an idea, the repeaters that I work with are what we call the most expensive ones, which are audio ones. But let's take a look at, again, I hope I answer your question on that. Let's look at baseband. Now, this is exactly what the Tissers will do. They will take that signal in a repeater setup and break it down to the baseband portion. That's how good they are. Of course, you're using 4 pieces of equipment. Normally, they come in pairs. So that's 2 sets of Tissers that you are having to use. Now, the nice thing about this is you could take out of the one Tisser, run it into a multiplexer, and do all kinds of stuff with it. Excuse me. And then use another multiplexer to send out or do drop-ins or, add or take away a traffic. And it gets quite busy with that. When I say busy, is you've got a lot more stuff that you need to add to in order to get the drop-ins. And of course, the last one, which is a full audio repeater. And when I say that I've dealt with audio repeaters, what we would do is one piece of equipment would take it all the way down to audio, and we would use the Vox voice activated transmit to the other one so it would retransmit it on a different frequency and vice versa. So we were breaking it down into the audio portion. Of course, each one of those base stations is between $3,000 and $5,000. So you were using two of them to do that. Again, really expensive. Limitations of repeaters, big time. Distance, equipment capability, terrain. And the big one, needs of the communication network. I like to say money talks, BS walks. So in other words, if you really needed it, you're going to find the money. Now, contrary to belief, it's not the base that comes up with the money, it's a squadron that needs the communication. And of course, you know, there's base stuff and then there's deployment stuff. The big thing is, you know, when you're looking at all these limitations and repeaters, how far do you want to go? That's a distance. What's the equipment capable of doing? If the distance doesn't equate to the equipment capability, how well do you need that comm? Because you may have to buy all new equipment that does a little bit better. Terrain. Do I need to get up and over a mountaintop, or do I need to transmit over, you know, a plateau or whatever? Noise factor. Again, this has everything to do with the style of the type of repeater. With frequency division, in other words, that's at RF, you are looking at 8 consecutive links before noise overshadows the information that's on it. TDM, which is basically the baseband, you're looking at 15. So that's how many links that you can do in there. But then again, 8 links versus 15 links, what's the capability? Can I get better equipment, or is it a short distance? And let's just say it's got a lot of terrain to cover. So again, goes back to the limitations of the repeaters as to how many links that you want and what you're going to use. So we've gone over line of sight principles, repeaters, limitations of repeaters. Any questions? All right, let's go to the next one. That was 4 alpha. Next one is 4 bravo. We're going to identify basic facts about, good grief, about tropo theory. Give me a second. Let me get this brought in. Okay, there we go. So get right to it. Yeah, we're going to have some beyond line of sight. Now this one's going to deal nothing with tropo scatter. So when you take a look at block 4, we just touched upon it. So we're going to look at tropospheric communications, antenna terms, and tropospheric antennas. This is what tropo does. They call it beyond line of sight. I disagree with that. It's more over the horizon. It doesn't go that far when you compare HF and SATCOM. Now, SATCOM has this, you know, hey, we're long haul. Well, that's true, but you shoot the satellite down, you're done. With HF, it's consistent depending on the time of day and what's happening in the wonderful world of the ionosphere. But you shoot a satellite down, it's going to take a very long time for that satellite to be shot back up in the air. So with tropo, I like to classify it as over the horizon. it's going to use the tropo, but if you take a look at, the science, like NOAA, NASA, some of the science portion, and I say science, we're talking credible websites, normally .org, .gov, things that you would do when you're in regular college and you're trying to do a term paper. They want you to do credible websites. So you just can't go to .com and say, oh yeah, it uses this. Well, with Tropo, they always classify it as a transitional zone in between the Tropo and the Stratus. Convergence zone, I think, is the actual name of it, where it's not quite the Tropo and it's not quite the Stratus, and it's a very thin layer. That's where most of Tropo gets refracted back down to Earth. We've got this diagram set up, and you can see where the refracted energy happens. It's right around the edge, the top part of the troposphere. Again, that's that convergence zone where we can refract that energy back down. Now, there's not a whole lot of that energy that does get refracted back down because most of it just goes right out the atmosphere. So you really got to be very sensitive with the transmitting and receiving antennas. They got to be very good at what they do. We look at power for TropoCom, anywhere between 300 watts to 50,000 watts. And the frequency is about 350 megahertz to 8 gigahertz. Now, when you look at this figure, 595 miles, this is an old figure from, I would probably say, about 10, 15 years ago. But if you look it up, it's anywhere between 580 to 610 miles. Why they picked 595, I have no idea. I think it was just in the middle. But that's fixed. In other words, you're probably producing 50,000 watts to get it 500 or 600 miles. That's a lot of power. It's a lot of consumption of energy to do that. Is it consistent? It's pretty consistent. Now, if you're dealing with tactical, like those rabbit ears we showed you earlier, that's a tactical thing, maybe 150 miles, and you're probably dealing with maximum 300, maybe 500 watts. The last thing you want is you do not want to become a target. What does it mean by that? Well, normally, if you're deployed, even though you're probably behind the lines a little bit, notice that keyword there, a little bit, when you transmit, you're putting out a signature that the enemy could probably see. So you just became a target because they don't want their information being sent back to where we can exploit their weak spots. We have something called scatter volume. This scatter volume looks just like this. Scatter volume is the area where it's common to both antennas. We also classify it as common volume. So those two are interchangeable. Again, it has everything to do with the antennas. In this case, the receiving one. We have something called a diversity system. I'm going to try to explain this to you, but it'll be easier once you see it on the TISR or the Jerk 239, whatever you want to call it. Polarization. You know that between nonlinear antennas, both vertical and horizontal, that they just don't talk to each other. You got to have vertical to vertical or horizontal to horizontal. Excuse me. The idea here is the way this is going to work, the frequency, you're going to have two different frequencies. You're going to have a separate transmit, you're going to have a separate receive, and those two will be no less than 200 megahertz apart. They have to be more. They have to be in that 300 to 400 megahertz apart to really get good. But you can get them 200 megahertz apart. It's just not, how do we say, that's the minimum would be the best. So you want to have at least 200 apart. You want to be more realistically. So those two play in with each other. Why? Because the tissue, if you take a look at your cut sheets and you put site 1 versus site 2 side by side, you will find out that your transmit frequency is the same to the distant receive frequency, and their transmit frequency is your receive frequency. Your antenna waveguides will be opposite in polarity, and that's so you don't interfere with each other. So not only are you 200 megahertz apart as a minimum, you also have to be the vertical versus horizontal. Next up, we have angle. Angle being, okay, where are you in the world? You know, how far are you out? I need to angle my dish to get the best possible signal. Next up is space. Well, angle, you could actually say DirecTV or Dish Network. They do have azimuth or azimuthal, in other words, 360, versus what's your elevation? So elevation would be that angle, as well as azimuthal, because you can have it at the correct angle but pointing in the opposite direction. You ain't going to receive it or transmit. Next up is space. How far apart are your antennas? When you guys go out and put your tissers up, you're probably going to be in a hallway or maybe even outside, but you're still not far enough apart. Truly see your receive signal level. In other words, you're probably going to be saturated like crazy. The object is you want to be far enough away to where you can actually adjust your dish, both azimuthal and elevation wise, in order to be able to communicate with each other well. And that's when you're adding the multiplexer to it. So all four of those have a play in how things work for your tisser. And Tropo needs that diversity signal or diversity system in order for interference to be cleaned out enough to where we can receive and transmit the signals. Here is your common volume. Can also be classified as your scatter volume. Takes a look a little bit about the scatter angle and how you can get it and where the refraction is going to take place. We have a couple of these nice words, which are reciprocity, directivity, and gain. Reciprocity you had back in block 4, using the same antenna, and it's going to transmit and receive well. You got directivity and gain. Okay, the higher the directivity, the higher the gain. The lower directivity, the lower the gain. In other words, a Yagi antenna, which is unidirectional, versus an omnidirectional. So you're probably going to get more distance out of the Yagi pointing it at each other than you would if you had a whip antenna. Next up is frequency. You guys did the mathematical equation for wavelength versus what an antenna is. Just remember, higher the frequency is smaller the antenna, and the lower the frequency is the larger of the antenna. We have the type of antenna is dictated by the radio path. In other words, we're going to be looking at two different types called the horn and parabolic. Why? Because they don't waste as much RF energy. Very directional. So we look at the horn. This is the most simplest. Flared aperture, impedance matching. Goes a pretty far distance. We have the parabolic, which we describe as the dish network or DirecTV. The idea is we're going to transmit and receive in two different directions. It says size and gain are directly proportional, not to be confused with the antenna. Okay? If you have a bigger dish, you're going to get more gain out of it. And we're talking a unidirectional here. If you have a smaller dish, it's not going to have as much gain to it. We use two different types. We have a front feed and rear feed. Parabolic is normally the front feed. It has a center fed or offset. We got a rear feed. We have two different types, a Cassegrainian and a Cutler. Let's take a look at those. So here's the front feed, center. You can see it's pretty darn close to the front. And then you have an offset. Now you guys, when you come into Jones Hall for your labs, you'll be able to see off to the side the particular antennas that the Block 9 is going to be using. This is an offset. We also have something called a Cassegrainian. I wanted you to take particular attention. The antenna is on the back of the dish. The subreflector is taking the information that's being reflected off of the parabolic dish and focusing in on the antenna. You can see by the diagram on the transmit path, just reverse it for receive. It's a parabolic subreflector that's on the top there that you see that is focusing all that energy to the antenna into that waveguide. We have a Cutler, which is a rear feed. This is what we will be using when it comes to the Tisser. It uses this waveguide that has two flat metal reflectors on it. Now the difference between that one and the parabolic looks like it is in the same direction as the regular dish is. In other words, you have a dish here and a small dish on top of it. This one actually has, coming off of the dish, you have two metal reflectors that's going to channel through the waveguide to the antenna. Kind of crazy the way it works. So we look at tropospheric communications, antenna terms, and tropospheric antennas. That was pretty quick, wasn't it? All right, any questions? Comments? Complaints? Oh, customer service just closed.